Okay, now I want to speak about alternative characterization of tree width and pathwidth for graphs. This does not have direct algorithmic applications, but it's kind of cool stuff, especially if you've never seen this before. And in the spirit of the time, I'm going to speak about, uh, you know, how to, guarantee that a group of people do not have coronavirus, okay, because it seems relevant. Okay, so we have a graph, G, okay, and there are vertices. The vertices are people, and an edge corresponds to two people that are in contact. Think about those people being in contact because, they work in the same office, or, you know, they're in the same family, or, uh, they go to the same grocery store, whatever, right? They interact very frequently, okay? And we would like to guarantee that the graph does not have, none of the people in the graph have corona, right? Now, so of course one way to do it is of course put everybody in quarantine, but that's expensive and not very effective. So we would like to do something a bit more efficient, right? So the basic idea is that we are going to look for the minimum number of people we need to put in quarantine. Okay. So the rule of the game is the following: we are going to put a group of people in quarantine. Let's say these three vertices initially, right? And then, after a while, they are not sick. Okay. And now, we can move, we can once the wait period is over, we can take one of the spot in quarantine and give them to somebody else, put somebody else in quarantine. For example, I can put this vertex in quarantine. Of course, at that point I lost, right? Because if this vertex had corona, then this vertex also got corona, right? So that's not good. So we should not be doing something like that, right? We should be cleverer than that. So the rule of the game is as such that the rules of the game as such is that I'm allowed, if I remove somebody from quarantine and they're adjusting to somebody that might still have the disease, then, this person immediately gets the disease again as far as we know, worst case analysis, and then there is nothing we have to quarantine them again, okay? So instead, we would like to find a schedule such that once a person gets quarantine, it's guaranteed to be separated from every later on sick people, right? So in this case, for example, I can do the following, right? So the red group is the first group, right, of quarantine, and then maybe I should do it like that. What I do, I move the quarantine here, right? So I move this person to quarantine, right? And what do I do now? Well, now I move this person to quarantine, right? And then I move this person to quarantine, right? So this is my second quarantine, and the important thing is that those three people that were first in quarantine are still safe, right? Because they didn't interact with anybody sick during this process. And now, now it's pretty easy, right? What remains to be done, right? We can quarantine this, oops, sorry, move this to this, quarantine this, and after, so now we're quarantining this group, right? Uh-oh, there was an edge here. Let me add it back. So we quarantine this, then we quarantine, we move this to this quarantine this, and then we quarantine this, and now we are done, right? We had removed the coronavirus from the graph. Okay, so it's natural to ask, as such, how many quarantine spots do we need to clean the graph? Okay. So this is known as graph searching. And the way it is described in the book is slightly different, right? So the way they describe it in the book is that you have a graph as before, and you put guards in, right? And now think about the edges as being pipes, okay? And now the idea is that you want to pick again, you want to find a schedule of guards, right, to guard the graph. And the name of the game is that now the edges are tunnels, so if you want pipes, and there is pipe, there is bad gas in all the edges of the graph, and an edge gets decontaminated, right, if both its endpoint belong to both its edges are being guarded in the same time, right? So the question now is, again, to find the schedule of the guard such that, all the pipes, all the edges, the gas is clean. And again, if you leave a vertex connecting a clean edge and an unclean edge, you leave the vertex unguarded, then the bad gas leaks back into the edges, right? And essentially, if you think about the way I defined it, I was a bit cavalier earlier. So think about whenever I said I move a guard, I move the quarantine from one vertex to the other. Just think about it as using two guards, right? So what I described here, in fact, is, to do this cleaning under the gas definition, I need, 4 guards, not 3 guards. But it's the same thing, right? Plus minus 1, that would be quite common. Okay, so under this model, the question is, how many guards do you need? And before going any further, we need the theorem of Lopakhin, theorem of Lopakhin. So this theorem states something quite surprising. It says that recontamination doesn't help. Namely, if you can clear the graph with k guards, then you can clear it in such a way that no edge gets recontaminated, right? Which is a very useful property. It really means that it's a kind of a monotone process. You're cleaning the edges in a monotone process, and right, and you don't have to worry about it, which is kind of a useful property. Okay. Okay, and now we want to define this notion of interval width of a graph. So interval width of a graph is intuitively it is the smallest width interval graph that contains G, right? So interval width of G is equal to the minimum of the width of G prime such that G prime is an interval graph and G contained, G is contained in G prime. And here W of G prime is just the maximum size clique in G prime, right? So it's the clique number. Okay. Okay, so so interval width, so to begin with, if you take so what is an interval graph? To remind you, an interval graph is just, you have the real line, right, and you take intervals. Every interval corresponds to a vertex, and right, and two vertices intersect. Two vertices have an edge between them if the corresponding interval, there is a point where the two intervals intersect, or namely there is a value of x such that it contains both intervals, right? So and of course this makes the definition of interval width is well defined, because you can of course take all the vertices to be intervals that contain all the, contain the same value of x, like the 0, so you can get the full clique which contains all graphs. So this is well defined, and in fact for interval graph it's not hard to prove that the largest size clique corresponds to the deepest point, right, in the set of intervals. So the two definitions are equivalent, and essentially what this interval width of a graph says is that this is the minimum depth of the interval graph that contains the original graph. Okay, and now we need we are ready to state our theorem. So theorem. Okay, so this theorem states the following: that essentially those the following three measures are equivalent. The search number, right? How many guards you need to decontaminate the graph, the interval width, and the pathwidth of the graph. They're all the same essentially, plus minus 1. So so some of those properties are easy to see, right? So the fact that, let's see, so this node search number being at most k, implying that the interval width of the graph is most k plus 1, this is not very hard to see once you have this claim by Lopakhin, right? So 1 to t to 2, right? So the claim by Lopakhin says, okay, take this schedule of decontaminating the graph using k guards, and we now are assured that no edge get recontaminated, right? So we can really think about it as a sweeping process, right? So in particular, you can think about every guard, right? You can number the guards, right, as you move them, and for every vertex, you can look on when it was, it was occupied by a guard, right? Now the problem is intuitively is that you might have a vertex that the schedule dropped a guard there, right? Then the guard went somewhere else. And in fact, this vertex can be recontaminated, right? And then what happened was that the guard came back, right? And so a vertex might be occupied and freed several times, right? But the trick is to use this Lopakhin theorem that says that we can change a schedule into an equivalent schedule such that no edge get recontaminated, right? What does it mean? It means that we can look on the first time the first time this this vertex got occupied, right, such that an edge around it got cleaned, right? So, you know, it might be that this vertex got occupied and unoccupied several times before that, but no edge got cleaned. But now one of the edges adjacent to it got cleaned, right? Which means that the other endpoint was also, there was a guard there. And now, the important thing to observe is that once we remove this guard, right, it cannot be that any of it adjacent around this vertex, when we remove the guard, it cannot be that any of those edges are contaminated, right? Because if they were contaminated, then this edge that was clean would get recontaminated. And we said Lopakhin theorem guaranteed to us that this doesn't happen, right? Which means in particular that once one edge gets clean, when this vertex get unoccupied, it never needs to be occupied again, right? If it gets occupied again, it's a waste of time. We can just skip it, right? So this in particular implies that in this new way of thinking about things, you know, a vertex get occupied once and get unoccupied once. In particular, we can just, for this vertex V, we can write down the interval over time when it was occupied for the first time and an edge got cleaned, and then the time when it was unoccupied immediately afterwards, and this is the time of the interval that corresponds to this interval, right? And now it's very clear that, so we do that, right? And now it's easy to verify that we get a set of intervals, right? We get a set of intervals, and now it's easy to verify that if you know, if you have an edge in the graph, then there must be two intervals. The two intervals that correspond to the two vertices must intersect, right? And furthermore, this interval has the property that since it corresponds to time, right? Any point that the axis here is a time axis. Since we're using k guard, there is no point where there are more than k intervals intersecting a value. Namely, the depth of this graph is k, and as such, the click size of this graph is k, and the interval width of this graph is k. The maximum size of the graph is k. So this implies 1 to 2. Okay, so that's good. Now, the second claim, the second to the 3 is in fact an easy claim, right? It says that if we have if we have an interval width of g is k plus 1, then the path width of g is at most k. But this is immediate, right? Because if you think about it for a second, and the reason is because take this supergraph of interval width k plus 1, so it's just an interval graph, right? And sweep it from left to right, right? So you have the, you know, as before, we have, if you want the time axis, and take a point and start moving it continuously from left to right, right? Every time you enter an interval, right, every time in point in time, you have a set of intervals that intersect your point. And this is just going to be your set, your bag size, right? So every time that you move from left to right, a bag either get, you know, we get different bags. For every point, you know, consecutive times where something change, you know, either the bag add one point or delete one point. And clearly, if the maximum depth is k plus 1, then the bags we get are k plus 1, and we get a path, you know, a path decomposition of this interval graph. And this path decomposition, the maximum size is k plus 1 of the sets of the bags. And to remind you, path width is 1 minus the maximum size of the set. So this is 2 implies 3. 3 implying 2 is also easy. 3 implying 1 is also easy, right? Because what is 3 implying 1? 3 implying 1 means we have a bag decomposition, right, of path with k. You know, we have this path, and it covers the graph, But you know, this path is now ordered in natural way from left to right, and we just make the we can take this path decomposition, turn it into a nice path decomposition, right? Nice path decomposition, the difference between two consecutive bags that most one vertex, right? So so as such, and all the edges are, every edge belongs to one of the bags, right? So all we have to do now is to move the guards from bag to bag to bag. Clearly we, at every point in time, we need at most k plus 1 node guards, and the whole graph get swept, and clearly an edge cannot be recontaminated, right? Just by definition of the graph of the, you know, the pathwidth. So let's complete the proof. I hand waved it, but in fact my hand waving I think is correct. So that's a nice proof.